There was waters, right?
Yeah, I just said,
Okay.
this is more than I thought you guys were getting.
Hello?
Hello.
Hi, everybody. Sorry, I'm just getting the layer going. We were working on a worksheet, right?
Is
Yes.
it the one about like the car?
The car?
But one of the problems was like a car dealership.
Wait, what's Leif doing in here?
Rafe, you're early by an hour.
What time is it?
Back to sleep.
It's 11, buddy.
Fuck. All right. Hey guys.
That's so funny. Oh my god. Oh, Leif.
I was like, car dealership? What?
I thought he was messing with us.
People that like crashed the Zoom classes.
Right, yeah, right.
I was like, what?
I thought he was just trying to figure out where we were.
Yeah, that's what I thought. I thought he was just like messing with Leif.
That's so funny. Let me just I'm trying to find our layer that we were on, but we were working on a worksheet anyway, right, guys?
Yeah.
Yeah.
Okay. So keep working on the worksheet. Let's, and as you go, please let me know how you're doing. And you know, which, you know, as you do the problems, show the answers. Well, I try to find our layer. Can't find it. Oh. There we go. Okay, let me share the screen again so that you guys can see the layer that we were looking at last time.
Ooh, an actual receipt.
Oh, wow.
Don't get that when they
Let me know when you finish stuff, okay? Show me what you got.
Hey, Shank.
Yeah.
I got 1 over square root 2 pi for number 2.
Okay. So, I told you guys to do that, and then I don't even have the answers in front of me. Hold on. Just a minute. For number what?
2.
Number 2. Indeed. Anyone else have stuff to show me?
I got the same answer as Jeff for number 2, and I'm working on that.
Yeah, me too. I'm working on 3.
Okay, good.
Dr. Shank,
Mm-hmm.
I'm a little confused on how to approach the integral for number 3.
Okay.
So I've gotten to the point where you pull the 1 over square root of 2 pi out, and then
Yeah.
it's just 1 over 2 pi.
Yeah.
Integral of e to the I kx. I'm not really sure like what to do with that.
Right. So this is the integral formula for the delta function, right? It doesn't. You don't actually have to integrate it. It's an integral formula for the delta function. That's what you're trying to derive.
Okay.
That make sense?
Yep. Shank. I think I have a number. I think I have an answer for number 3.
Okay.
All right. So I got 2 pi, or 1 over 2 pi, e to the I k to the infinity minus e to the I k minus infinity.
Right. Yeah. You don't want to actually do the integral. Just write because the question asks you to derive an integral formula, which means you keep the integral.
Okay.
Yeah. You don't have to do it. Yeah, because it's kind of nonsense, right? When you think of it that way, right?
Okay. So just leave it like the 1
Yep.
over
Yep.
pi e to I to the kx.
Well, the integral. Minus
Yeah.
infinity. Yeah. Does that
Okay.
make sense?
Yeah.
All right. Let's just spend about 4 more minutes on this. Two more minutes, guys. Try to finish up. All right, well, we should stop and move on with what we're doing. So, okay. Everybody have a feeling for what the delta function does?
Yes.
Good. All right. If you can, turn on your video. It's just kind of hard to lecture when there's nobody. I can't see anybody. Thank you. Okay, cool. Thanks. If, it gets too laggy or something, we'll deal with it. All right, so we're looking at this delta function potential, and so that just means that there's basically a spike, right? So the potential gets really infinitely high at a certain place, right? And everywhere else it's 0. All right, so I'm gonna get a new layer so we can look at that specifically. So what this particular delta function looks like is that it's going to be negative. It's not going to be a positive delta function, but it's going to go down instead of up. So it's going to go down to minus infinity, but all the same rules of this are the same. You just stick a minus sign in front of it. Okay? So let's take a look. So we're going to say our delta function potential and that's going to look like this. V of x is equal to minus alpha, some constant, times delta of x. Now, if it's delta of x like that, where is the spike?
Zero?
Yeah, it's at 0, right. So, and it's negative. So if we look, we're going to draw the potential. So here's the potential. Then there's this really, really, really long, thin spike thing here. I can't obviously draw it all the way down to infinity. But right here at x equals 0. Right? Okay, and everywhere else it's 0. So this is potential, right? Oh, sorry, that was bad. What I meant to do is, let me erase this thing. I just gotta move it out of the way. I'm messing everything up. Hold on. And right here at 0, this is right, this is B. This is X. Right here at 0 is our spike. Okay. And then everywhere else it's 0, right? So it is 0 everywhere else except for that spike where it's minus infinity. Well, minus alpha times infinity. Yeah. Okay. All right. So for the TISE, if we write down the TISE, right? So this is what we got to do, right? We've got a potential. We got to solve the TISE. We have minus h bar squared over 2m. We have d squared psi dx squared. And then we have minus alpha delta of x, psi is equal to e psi. Now, the issue is that this thing is non-zero only at one place, right? So it doesn't really make sense to write down the TISE like that because it's 0 everywhere except for that one place. So it doesn't make a whole lot of sense to write it that way because we can't really do anything with it. We can't really solve it this way. So what we like to do instead of writing this down like this is to say we're going to solve in this region. So we're going to solve over here. For me, that's left. Right, so minus for minus x, and we're going to solve on the right at plus x, and then we're going to stitch them together. But over here on the left, before we get to the spike, there's no potential, it's 0, right? So the TISE just looks like this. Right, and on this side, it also looks like that. Right? It's only right there at the middle where it looks, where it has that spike that it's going to look different, right? Okay. So let's just solve for on the right or the left. So first let's solve for x less than 0. Okay? So we're solving on the left now. And I also want to point out here that if we look at our diagram here, right, the total energy is going to be up here, right? So if I draw this again, I have, you know, the spike, whatever. Then I have the total energy is going to be up here. So E total is going to be greater than 0, which is greater than V at infinity, right? Because V at infinity is 0. So this is going to be a scattering state, okay? Kind of like the free particle. It will be our second scattering state that we look at, okay? So, and it's not a given that E is greater than 0. We're just going to use the case when E is 0. And we're also going to look at a case where E is less than 0. So we're going to look at two cases. So we're going to look at E total greater than 0. This is case 1. And then we're going to look at another case down here where E is less than 0. Okay, E total. Oops, hold on. Let me erase this. It's scattering. I'm going to move your guys' pictures right away here. So we'll write E greater than 0. That's a scattering state. And then E total less than 0 is a bound state, right? By our rules for bound and scattering states from before, okay? But we're going to look at case 1. So we're going to look at case 1. I'm pretty sure we're looking at case 1. Are we looking at the bound states? I got to figure out which one I want to look at first, actually. Yeah, I think I'm looking at the bound state first. So let's look at that bound state first. We're going to look at case 2. Okay, so we have E less than 0. Okay, so it's bound. Okay, that's what we're going to do first. And we're doing the left side. Okay. All right. So let's write out left side now. So left side, we have the TISE minus h bar squared over 2m d squared psi dx squared is equal to E psi. And I'm going to just pull all these constants over here. So I'm going to say d squared psi dx squared is equal to minus 2m e over h bar squared psi. Okay, and then I'm going to rewrite this as a constant, and I'm going to write this. And notice right here that if E is less than 0, then there's a minus sign here, right? This whole thing will be positive, right? This whole thing will be positive. So I'm just going to call this kappa squared, not k squared, but kappa squared psi. Okay. Either one you want to do. Okay. So we have kappa squared psi, where kappa is this stuff. Like I said, kappa, let's write down kappa. It's the square root of all that stuff, right? Square root of 2m e. Hold on a second. I got to erase. Square root of minus 2me over h bar squared. And so that's the square root of minus 2me over h bar. And again, inside here, that is a positive quantity because E is less than 0 in this case, okay? That is not going to be imaginary, even though it has a negative sign under the square root, okay? Just to be aware. All right, again, we have one of these differential equations where we have the second derivative of something is proportional to something itself, and we should use exponentials, okay? So we're going to put psi of x as a guess, e to the lambda x. And now taking the second derivative, d squared psi dx squared is equal to lambda squared e to the lambda x. So let's plug all that in. So we have, plugging in here, we have lambda squared. Lambda squared e to the lambda x is equal to kappa squared e to the lambda x. Then we get rid of the lambda x's, and we get lambda is equal to plus or minus kappa, right? So, which of course is just plus or minus the square root of 2 minus 2me over h bar. Well, we're just going to leave it as kappa, I think, for a while. Okay. All right. So now I can write down my general solution. Psi of x is equal to some constant e to the minus kappa x plus another constant b e to the kappa x. Okay, cool. And now we can at least think about what conditions we need to have on psi. So now remember, this is just for the left, right? So at minus infinity, when x is minus infinity, what happens to psi? I should probably say this is psi left, right? Psi left. There we go. What happens to psi if psi left, that is, if x is minus infinity? What do you think?
It's 0.
Okay, what term gives you 0?
I don't know.
What do you think it should be?
I don't know. Well, because it's x is 0 everywhere but at 0, right?
Right, but that doesn't necessarily mean that psi has to be 0. I mean, you're right that psi should be 0, actually. You said 0.
Yeah.
Because psi is not 0 to infinity, it's just not going to normalize. So if we can make it 0 to infinity or an n minus infinity, it would be better, right? Otherwise, we have to do some fancy footwork like we did before with the free particle and have to put it in a wave packet or something. But here, what if you literally plug in minus infinity into that function? What do you get on the first term? What's the first term give you?
Would it give you minus infinity?
Okay, so why minus infinity?
Because of the minus k, due to the minus k. But
Okay, well, I literally on your piece of paper write down e to the minus kx, and then write down e to the minus, and then put minus infinity in for x, and then what do you have?
It's e to the minus k or kappa minus infinity. So would it end up being positive infinity? E to the minus or e to the positive infinity?
And what is e to the positive infinity?
Infinity?
Yes.
Okay.
What about the next term?
And then it's the opposite for the next term, right?
Or what does it opposite mean? What do you mean?
It's negative infinity.
What's e to the negative infinity?
Negative infinity.
No.
No, wait, what?
Mm-mm. Think of it this way: it's 1 over e to the minus e to the minus infinity is 1 over e to the infinity.
Oh, okay.
So what is it?
1 over infinity? Is that what it? No.
Well, I
No.
mean, yes, 1 over infinity. But what is 1 over infinity?
Infinity?
No,
I don't know, man. Wait, it's
0?
0.
it's 0. That's
Yeah.
right. E to the minus infinity is 1 over infinity, which is 0. Right? It's what we call a dying exponential, right? It dies off as you approach infinity. Yeah? Got me? Okay. So which one of these terms, remember A and B are up to us pretty much, right? This is kind of a boundary condition, right? It's kind of saying, hey, you really can't have infinite psi at minus infinity. So which one of these A or B can we set to 0 to make our function not be infinity? Which one was infinity again?
A.
Mm-hmm.
So we set the A function to 0.
Yeah, well, A is just a constant.
Well, like that.
Yeah. Right. Right. So then we do that. Then psi L of x is b e to the kappa x. Now, this function, right, this would be a problem at x equal positive infinity, but this solution isn't for that, right? This solution is only for the left, right? Correct, I mean? Yeah? Okay. So, all right, so far so good. Let's see, let's do for x greater than 0, okay? For x greater than 0, so we have d squared, so x greater than 0. We have d squared psi dx squared, and I've already moved the stuff over, is equal to kappa squared psi. And again, we're going to do psi, we'll call this psi right. This is also for psi right. Psi right is e to the, gamma x. And again, d squared psi right, dx squared is gamma squared e to the gamma x. So we plug everything in, and again, we're going to get a very similar thing, right? So let's plug it in. So we have gamma squared e to the gamma x is equal to kappa squared e to the gamma x. So those go away, and of course we get gamma is plus or minus kappa, once again. And so we can write down psi right is equal to, f e to the minus kappa x plus g e to the plus kappa x. And now let's think about positive infinity. I want you guys to work it out. Tell me which one of these needs to go away, because we don't want psi to be infinite at infinity. We'd like it to be 0.
Wouldn't it be g this time? The g function?
That's right. G would have to go because e to the kappa infinity is infinity, right? But e to the minus kappa positive infinity is 0. That's nice, right? So we get rid of this guy. And so we have psi right is equal to f e to the minus kappa x. Okay. I'm going to do some erasing up here. Okay. Let me see. Wonder if I duplicate the layer, will that be a better thing to do? Let me just say for a sec, okay? Yeah. Yeah, and then I can erase and keep the whole layer anyway. All right. I'll rewrite that kappa, but it's in the way. Okay, just a sec. I'm going to write our psi left is b e to the kappa x, and psi right is f e to the minus kappa x. Hold on, guys, for 1 second. Sorry, try to manage kid at the same time. Okay. All right. So we got our kappa, our left side, right. Sorry, I've got to erase a little better here. There we go. Okay. All right. And now we know that there are 2 boundary conditions for this, right? I mentioned one when we first started looking at the ISW, right? So there's boundary conditions that are general boundary conditions for quantum. Okay, and so those are, so one, psi has to be continuous everywhere. And we used this one in the ISW because we said, look, the potential is infinite outside the well, and therefore psi's got to be 0 there. And that meant that it had to be 0 on the boundary of the well, otherwise it would be a discontinuous drop to 0, right? So we used that boundary condition for both the left and the right sides of the well to solve for psi, okay? We just didn't really, talk about it too much. And then 2, this is a little different one. The first derivative of psi with respect to x has to be continuous. Everywhere, except where v is infinity. Okay, and we have one of those places, plus or minus infinity. We have one of those places, right? We have a spike that goes all the way down to minus infinity. So at that point, right at x equals 0, the derivative can be continuous. It has to be continuous everywhere else, but right at that point, it can be discontinuous. And in fact, it is discontinuous. But psi itself has to be continuous everywhere. Okay, so if they can't jump from one value to the next, right, over, at a point. Okay, so the first boundary condition, the number 1, we can actually implement now because, and I'm going to erase more down here because we don't need this now. Because right at x equals 0, we have a point where we have on the left, we have this guy, and on the right, we have this guy. And at 0, they have to be the same, right? Because right at 0, there can't be like a jump from one to the other. Does that make sense? So let's think about, just for a second, let's just think about on the left. Let's say, kappa was 2, okay? On the left, when x equal minus 1, we have e to the minus 2, right? So let's say let's just say kappa is equal to 2, just for an example. Kappa is 2 at x equal minus 1. We have to use the left solution. And we get psi left is b e to the minus 2, right? And then on the right side, and then imagine now making x go towards 0, right? So x equal half, minus a half, this would be, e to the minus 1, right? But at 0, psi left is just b, right? And now think about on the right side with kappa equal 2, at x equal 1, psi right, we have to use psi right for that, is f e to the minus 2, right? And at x equals 0, psi right is just f, right? So at this point, where the two things meet, we could make them equal by literally just making b equal to f, right? If we did that, then they're going to match, right, at 0, aren't they? Does that make sense? Okay, so now I can write down, after implementing my first boundary condition to make sure they match, I can write down that psi is equal to b e to the kappa x for x less than or equal to 0, and again b e to the minus kappa x for x greater than or equal to 0, and at 0 it's the same, right? So okay, so we've got our size. We do not have b yet. And to get b, we actually have to do a little bit more work. And I think what I'm going to do is just see if you guys have any questions. Have you been working on your problems? Right, remember it's next Wednesday, right? That you got to present? Okay. So make sure that you've looked at them, worked on them. I know one of you has gotten in touch with me, which is great. You know, working on them early because you don't want to be like scrambling to try to figure stuff out, right? You want to be able to talk to you about your problems before Wednesday, and that's only a few days away, really. Okay. All right. I think I'll let you go a little bit early today because I don't want to start the next thing, which is a little bit long. Okay, guys?
All right.
See some of you in MATLAB.
Yeah, see you Monday.
See you Monday, yeah.